There is an insect that feels a flower's electric charge from the air, and almost no field guide says so. What we are about to show you was confirmed in a laboratory a little over a decade ago, then quietly left out of nearly every documentary since. The insect is the honeybee, the same striped, ordinary bee you have watched cross a garden 100 times without a second thought. We think we know it. It flies, it lands, it drinks nectar, it carries pollen home. That story is true, and it is also missing its strangest part. A flying honeybee is not electrically neutral. It carries a charge, a faint positive voltage built up in the air, and it can sense the opposite charge waiting on a flower before a single hair touches a petal. For a long time, biologists insisted this was impossible, that sensing electric fields belonged to sharks and rays underwater, never to an insect in dry air. The honeybee did it anyway. By the end of this video, you will understand why a bee can read a flower like a charged page, and why that page rewrites itself after every visit. Follow that charge back to where the honeybee actually works, and you land in the open air of a sunlit meadow, a few feet above the ground. Apis mellifera, the western honeybee, lives almost anywhere flowers do: orchards, hedgerows, rooftop gardens, dry scrubland, alpine slopes. It is one of the most widespread insects on the planet, carried by humans to every continent except Antarctica. A worker leaves the hive when the air warms past roughly 12 degrees Celsius, and she will fly several kilometers in a morning, visiting hundreds of blooms. The conditions that favor her are the conditions that build her charge: warm, dry, still air, the kind of clear afternoon when static gathers easily. Each wing beat, each brush of air against her body, strips away a few electrons. By the time she nears a flower, she is running a small positive potential, tends to a couple hundred picocoulombs, riding invisibly on her like a held breath. The flower below her is the opposite, rooted to wet soil, connected through its stem to the ground. Most blooms sit at or near the Earth's negative potential. Between the descending bee and the waiting petal, an electric gap opens, and something crosses it before she does. What crosses the gap is pollen, and to understand why, you have to look at what the honeybee is built from. She is an insect, plainly: 6 legs, 2 pairs of wings, a body in 3 segments. Nothing about her classification hints at a sixth sense, but her surface is the trick. A honeybee is covered in around 3 million hairs, and they are not simple bristles. Each is branched and feathered, splitting into fine side branches like a microscopic pine bough, which is exactly why loose pollen clings to her in golden drifts. That fur does something less obvious, too. Hair is an excellent insulator, so the electric charge a bee builds in flight does not drain away. It stays on her, spread across that enormous hairy surface. She is, in effect, a flying capacitor wearing a yellow and black coat. She is not a shark. She has no electric organ, no jelly-filled pores, none of the dedicated receptors ocean predators used to hunt by field. By every textbook expectation, an insect like this should be electrically blind. And yet the same hairs that catch her pollen turn out to be the antenna for something no one believed an insect could feel. Here is the moment that should not work, filmed in slow motion in a Bristol laboratory. A honeybee, carrying her flight charge of roughly 50 picocoulombs of positive electricity, descends toward a flower. She has not landed. She has not touched a single petal. And the pollen leaves the flower anyway. Grains lift off the anthers and jump up through the air, crossing a gap of a few millimeters to stick to her body before contact. It looks like the flower is reaching up to meet her. In a sense, it is. The bee's positive charge and the pollen's opposite charge pull toward each other across the open air, and the lightweight grains, barely held to the anther, lose the tug-of-war and leap. No bee biology textbook from the 20th century describes this, because for most of that century no one looked for it. Pollination was a story about contact, bees brushing against flower parts and dusting themselves by accident. The electrostatic leap turns that into something closer to attraction in the literal, physical sense. The flower does not wait to be touched. It hands its pollen to the charge in the air. But a leaping grain is only half the strangeness. The deeper question is whether the bee can feel the field doing it, and the answer is yes. The feeling happens in the hairs. When a bumblebee or honeybee enters the electric field around a flower, the field exerts a tiny force on her charged body hairs, and they bend, measurably, by a fraction of a degree, the way a single filament of hair lifts toward a charged balloon. Those hairs sit on nerves. Their deflection fires sensory neurons at the base, and the bee registers the field as a sensation, the same way you feel a breeze move the hairs on your arm. Researchers proved it the hard way. They built artificial flowers with controllable charges and showed that bumblebees could learn to tell a charged flower from an uncharged one, choosing the one that paid out sugar, then failing the test the moment the fields were switched off. The physics that makes this possible is the physics that makes it rare. Air is a poor conductor, which is why everyone assumed field sensing was for fish. But a bee does not need to conduct the field. She needs only to be charged herself and let it push her hairs. And there is a second message in it. When a bee lands, her positive charge bleeds onto the flower and alters its electric signature, leaving a mark that says recently visited. That altered field takes about 100 seconds to fade back, a fading do not bother sign the next bee can read from the air. No scent required. None of this is new. The honeybee has been reading flowers this way for almost as long as there have been flowers to read. Bees split from their wasp ancestors roughly 120 million years ago, in the early Cretaceous, right as flowering plants were spreading across the world. For all that time, charged bodies and grounded blooms have been leaning toward each other in the air, pollen leaping gaps, fields fading and resetting. The mechanism is ancient. Our knowledge of it is not. The honeybee itself was scientifically described by Linnaeus in 1758, and for the next 2.5 centuries, with the insect studied more closely than almost any other on Earth, the electric sense went unnoticed. It was only in 2013 that a team in the United Kingdom demonstrated that bumblebees detect and learn floral electric fields, and a few years later that researchers filmed the body hairs actually deflecting in response. One of the most observed insects in human history was hiding a sense in plain sight, on a creature kept in backyard boxes and farmed for 10,000 years. We had the bee. We had the flowers. We simply never thought to check the air between them. And once you know the sense is there, the ordinary garden starts to look very different. So why does almost no one know this? Partly because it is invisible. There is nothing to see, no glow, no spark, no organ to point at in a diagram. The whole exchange happens in the silent pull between a charged body and a grounded petal, over in a fraction of a second, written in a language of volts we are not built to perceive. And partly because the honeybee is too familiar. We long ago decided we understood it, filed it under pollinator, and stopped looking. The strangeness was never hidden in some unreachable place. It was riding on the most studied insect we have, in the gap of dry air above every flower in every garden you have ever walked past. The next time a bee drops toward a bloom and seems, for an instant, to hesitate just above it, she may be reading the charge, checking whether someone has already been there. She is not landing blind. She is listening to a field, in a voice no flower ever speaks out loud.